So there is one usual algorithm of which we always resort to immediately, a greedy algorithm. So if I say greedy, then how do we proceed with that? I don't have a BFS now for greedy. Take the highest degree. So greedy algorithm proceeds in this way. The existing online algorithm, I will tell you, online coloring. You are given a vertex ordering, so you have to fix an ordering first. Okay, take a fixed order, and you start picking up one vertex from that, and you start coloring it. Okay, so it's a very standard greedy algorithm that we go about. So you take a vertex, you color that vertex, and you look at its neighbors, right? Or actually we go from greedy, right? So suppose I am coloring, starting with first vertex, I color the first vertex with some color C1, and then I go to the second vertex, I see if these two vertices are adjacent or not. If they are not adjacent, then I can use the same color, right? So out of my color class, I will choose a minimum numbered color, like say 1, 2, 3, I can choose a minimum numbered color and color the second vertex, and so on. After ith step, if I want to color I plus 1th vertex, what do? We can just look into all the colors, the neighbors of this vertex vi plus 1, and see which minimum color is not being colored, which is left out in its neighbor, and choose that color, right. So this is a very standard greedy algorithm that we have. So using greedy algorithm, now let us look into this. Somebody has given me already answer for this graph, but still I will give you an ordering. So let us consider, say V1, V2, V6, V5, V3, V4. So with this ordering in hand, how many colors do I require? So what is the procedure that we are going to do? So we start with the color vertex V1. So I will just color this vertex with say V1. Next I go into V2. I look into it. V1 is adjacent to V2. So I cannot use the color 1, which is used already. So I need a new color. So I go into it and I give color 2. And next is V6, right. If I look at V6, I can use either of them, 1 or 2. So greedily I will always choose the minimum numbered color that is available. So 1. Next V5 comes. So V5 will require color number 3, right. And what about V3? 3 again. And what about V4? 2, right. So this ordering gives 3 colors, right. So one disadvantage of greedy algorithm here is that it does not give optimum solution always, right, because already we have seen that it requires 2 colors. 2 is enough for this, right. So for that again I can look at the ordering and I can just give you the usual sequential order. If I give V1, V2, V3, V4, V5, V6, this requires 2 colors, right. So I can just sequentially go about it. In fact, my greedy could produce worst coloring also. So if suppose I use this sequence, think of the third one. How many colors do I require for the third one? So as before, if we go greedily, we will choose for V1 color 1, V6 1 again, right, V3 2, V4 2, what about V2 3, what about V5 4, right. So here you can see that this greedy algorithm depends on the ordering of the vertices, whatever we are taking, right. So we should be cautious when we are applying greedy algorithm, and it not always gives us optimum solution. Okay. So how to overcome this difficulty? Yeah, better choice. So that's what I should be able to give a better choice of sequence. So, what should be that better choice? Always, like now I randomly picked up 3 sequences. I know one gives me color of 3, one gives 2 and the other one gives 4, right. So, what would be a better choice for coloring or for the algorithm to run sequentially? What would be the best ordering? Find in? That is a problem, you have to find it. So, one thing is we can try to overcome this trouble, like the first one, first option what he gave, do a BFS, do a level decomposition of your graph, okay, and give the vertex ordering from levels, right. Say suppose I have a level of, this would be my first vertex I start with, say this is n0 of a vertex v, 0th level, and then I have the first level neighbors in my BFS, right. So, this would be n1 of v and so on, and this would go up to the maximum distance, right, say some nk of v, right. So, now from here you can start looking at giving a ordering in such a way that you choose n0 of v followed by n1 of v in any order. Within the level it does not matter which order we are going to give. So, you can give in any order n1 of v, n2 of v and so on. Okay. So, this eliminates a possibility of having very worst case. Okay. Even then I will not guarantee this greedy will give optimum solution always, okay, but we can guarantee at least we will be in a better state. So, this is about greedy algorithm. So, with one final algorithm, let me one final result, let me go to the next coloring possibility. So, we have already seen chi of g requires delta plus 1 colors, right. So, this is a famous Brooks theorem which says there is a theorem by Brooks which states that if G is a graph such that it is neither an odd cycle or a complete graph. Okay. If it is neither an odd cycle nor a complete graph, then chi of G is going to be less than or equal to delta of G. Because these two are the special cases where we require delta plus 1 colors. Kn has n minus 1 delta, right. So, we require n colors, similarly C2n plus 1. So, this is Brooks theorem. I will not go into the proof, if you are interested you can look into it. Okay. So, in this direction I will put up a couple of questions for you to think for tonight. Okay. Can you give the vertex coloring number or the chromatic number of the following graphs? Say tree, if possible you can also tell me now also if it is quite easy. If I have a multipartite set n1 n say S partitions are there already, say kn1 n2 ns, each partition contains ni number of vertices. C2s plus C2s plus 1. So, what is the sum operation here between two graphs? How do you define? Joining, that is what, how do you join them, that is the question. So, you add, you have C2s and C2s plus 1 to every vertex of C2s, you connect it to every vertex in C2s plus 1. Okay. So, it is a simple plus, you just add it will be in between. If you see, if you think of these two as partitions, it would be complete in between, right. Every vertex from C2s is going to be adjacent to every vertex in C2s plus 1. So, in this slide I will also give you one more hint. Okay, I will leave it, we will talk about it tomorrow. How are they related? Chi of G1 plus G2 and chi of G1 plus chi of G2. Is it less than or greater than or equal to? So think about this questions. So next we will go into edge coloring. Okay. So edge coloring is another variation of vertex coloring. So what is the variation of variation in edge coloring? Anybody quickly? Okay, here we want to color the edges. A simple variation, guys. Okay, so the question now is, how many colors do we require to color a given graph? Okay, so that no two adjacent edges receive the same color. So when are two edges adjacent? When they have a common vertex, right? So how many colors do we require? So this is one famous graph we always have. So how many colors does this graph require for edge? Max degree. Okay, you have an option, delta of G. So here we will call again the minimum number of colors is what we are targeting to. Okay, so minimum number will be called as edge chromatic number or chromatic index. We also represent it by chi prime. Okay. Yes, how many colors do we require here? 4. He has given max degree. What is the max degree? 3. Then anybody else? Any other answer? So one is we require at least delta colors because every vertex is going to be incident on delta edges. So at least those many we have to look into, right? So this is a lower bound for chromatic index, that we require at least delta colors. Right? What about the upper bound? Can we connect anything like we did in the previous case with click? Here can we do something with that? Chaliye, before we go into that, okay, let me put up some standard questions. What about chi prime of Kn? The answer for this one which I have drawn, I will give you the colors. Say suppose I start with 1, 2, this could be 1 and 3, then since I have 1 and 3 adjacent to this, I can give 2, right. Since to this edge I have 1 adjacent, but 2 and 3 is also there, so I have to give 4 for this, right. So 1, 4, 2 is there, so I can give 3 here, right. So this graph requires 4 colors. What about the other classes? These are some standard class, we keep seeing them regularly, right. Bipartite requires max degree, so maximum of either partition you can think of. What about a path? You just have a path, right? Path is already an alternating sequence of edges. So how many colors you require for edges? 2. Come on, wake up. It's time up anyway. We'll finalize it. What about CN? Cycles. 2 or 3, same as before, right? It's either 2 or 3 depending on even or odd, right? And complete graph. Still wondering, you require n minus 1 or n plus 1. Simple, think of K3. K3, how many colors you require? K3 requires 3 colors. What about K4? K4 requires 3 colors. K3 requires 3 colors, right? So, what about K5? So, it is not a common number. First of all, you have to realize this part. It is not like your vertex coloring, it is standard n for any complete graph, but here it is not the case, right? Is it that difficult? N into n minus 1 by 2, wow, that is a good number. Can you tell me how did you come up with that?
Because first you choose one, then the other guy has one less option, then the other guy has 2 less options.
Who is the other guy?
The other remaining edges.
Why should it be? We are talking about proper coloring, right? Why you require n into n minus 1 by 2? Of course, if you require 10 colors, you can also do it with 11 colors or 12 colors, 13 colors, or n choose 2 colors, that is obvious. But in K equal to K in K4 you had 6 colors, but you could do it with 4, right? Yeah, you are right. I am just confusing you, don't worry. Okay. So, n minus 1 when n is even and n when n is odd. Okay. What about Peterson graph? How many of you know what is a Peterson graph? Okay. So, next I will touch upon one final bound that we want to talk about. So, we have seen that chi prime of G, the edge coloring requires at least delta colors, right. So, for the other upper bound, chi prime of G is less than or equal to delta plus 1. You require either delta or delta plus 1 colors, you do not have to go to n choose 2 obviously, okay, or n, either way. And this is for simple graphs. Okay. When you go in for multi graphs, this need not work. Okay. So, these results whatever we are talking is for simple graphs. So, in case of multi graphs, like when we say multi graph, when there are multiple parallel edges present in the graph, then what can we say about the coloring? What will be the bound, upper bound? Obviously, minimum is delta, we require at least delta colors, right. In the case of, we will forget about loops, think about in terms of multiple edges. How many colors do we require? Okay, this is Weising's theorem. For the proof of this, I recommend you go and look into any graph theory book because the lower bound is easy to see, we have already observed it, but for the upper bound you need to dirty your hands, you need to go in for multiple cases, you have to split all possible cases and do it. So, if you are interested, I would suggest you could look into Bondi and Murthy or even D still has. Okay, just for before I wind up, suppose given G is multi-graph with no loops. Okay, we will not worry about loops now because loops are a little misleading. Okay. So, if you have multi-graph with parallel edges, what would be the upper bound? It is not immediate to see, I know, I will just give you the answer. So, it is going to be delta plus mu, where mu is the maximum number of parallel edges present between two vertices. Okay. So, given two vertices, if we have k parallel edges and that is a maximum number, so that is what we would like to take into account. So, the upper bound would be delta plus mu of G. Okay. This is the maximum number of edges between any two vertices, because we are talking about maximum number of parallel edges obviously, because delta of G will take into account the from any vertex, right. So, there are more results in edge coloring, but we will not go into that. If you are interested, you can go further into it. The next type of coloring that I wanted to talk about was planar face coloring. So, with this we will stop for today. If